will see some examples on VHDL modeling. So like we have to design 2:1 mux using data flow modeling. So like in like you can see in 2:1 mux, there is two input, one select line and one output. So when the select line s equal to 0, then the output will be a, and when select line s is equal to 1, then output will be v. It is a basic behavior of MOS that we all know, or sorry, mux that we all know. So moving further. So as always, we first declare the IEEE libraries, a library IEEE, and use a library IEEE std logic 1164.org. So after that, we will create an entity. So we named our entity as mux221. So this is our entity name, and inside entity name we will declare our ports. So age and A, B, and S are input ports, and Y is an output port. So after that we will end entity, and after entity we will start with the architecture. So architecture behavioral of mux 221, the name of our architecture. So we will begin it, and yeah, you can see that like for s equal to 0, our output is a. So we will write the equation of y like not s and a, or s and b. So it means when s will be 0, so then output will be a. Like this will be this part will become 0 for s equal to 0, and when s will be 1, then this part not s, this will become 0, so output will be b. So like this you can write the code of 2:1 mux. So now we will see the 2:1 mux using when else statement. That was using simply data flow modeling, like simply writing the equation of mux. But here we will use when else statement. So the upper part will be similar, like library declaration, and after that entity declaration, and after that we will architecture declaration. So we will use like a when s equal to 0, else b. Means when s equal to 0, the output will be a, otherwise the output will be b. So like this we can define our 2:1 mux using when else statement. So and this is the third type of declaration, like 2:1 mux using case statement. So like previous cases, the upper part like library declaration and entity declaration will be same, but in the architecture declaration we will begin with and we will use process statement. So you know what is process statement. Inside the process statement we write the input variable by such input variable by changing which our output gets changed. So like here, if we change a, b, and s anything, then our output will be changed. So we'll write all these three, and we will begin the process statement, and we write the case statement. So here we are using case. So we named the case statement. So our case is s, and when s is 0, the output will be y equal to a, and when s is 1, the output is y equal to v. So you can see here, and after that we will end the case statement. Like case statement is opened at the last, so it will be closed first after case statement. Then after case statement there is a process statement, so it will be end process, and at last end behavioral. So you can do like that. So here we see the 2:1 mux using 3 methods. So all are correct methods. You can use any which you want. Now 3:8 decoder we will design a 3x8 decoder. So you can see the circuit of decoder. Like A, B, C, three are inputs, and it is G0, D1, 2, 3, 4, 5, 6, 7. These all 8 are outputs. So when A is 0, B is 0, C is 0, then D0 bit will be high and other bits will be low. Similarly, for case of 1, the D1 bit will be high and other bit will be low. So like that we can design the truth table of 3x8 decoder. So now we will see the code. So first of all, as always, we declare the libraries, and after that we create an entity, and entity name, we give the entity name like 3x8 decoder. We give the entity name 3x8 decoder, and up in the inside the port we will declare A as input port, and we take a steady logic vector. So like A bit we didn't take like A, B, C, three inputs. So we take a single input with three vector like A0, A1, and A2, and like output we take Y. So Y is an output port, and it is in vector. We take this also vector like 7 down to 0. So this is an 8-bit vector, and this is an 3-bit vector. So after that we will end the entity, and after entity, as always, we will declare our architecture. So architecture behavioral of decoder trick. This is our architecture name, and we will begin it, and we will process A, because we have take A variable only as input variable. So we will change A, then our output will change. So we will process A, and we will begin with same as we have seen in previous question of marks. So for case A, like when A 000, then the D0 bit will be high, like you can see here. When A is 001, then D1 bit will be high. Similarly, when A is 111, then D7 bit will be high. So likewise, we have covered all the cases of D0 to D7, and when anything like any other input comes, so the Y will be 000. So we make it a default case, and after that we will end the case statement. And after case, you can see here is process, so we will end process, and after process end behavior. So like that we can design any decoder. Like here we use 3 to 8. You can design 2 to 4 and 4 to 16. Any type of decoder you can design in the same fashion. So moving on the next part. Okay, now we have taken one example of sequential circuits. So D flip-flop. We all, as we know, like in D flip-flop, when D is 0, then the Q is 0, and D is 1 when Q is 1. It is simply when the clock, it takes the clock, then it becomes the same Q equal to D. And in case of when D is, when reset is high, the Q becomes 0. We know this. So try to write the code of D flip-flop. So first of all, we will import IEEE library. This is the thing we always do, and after that we will declare an entity of D flip-flop. So D flip-flop entity means the D clock and reset. These are the inputs we take, and Q is our output, and we will end the D flip-flop. So after that, after the entity, we will declare our architecture. So architecture of D flip-flop. We will begin the architecture here, and we will process clock and reset. So in after beginning the process, If reset equal to 1, then S equal to 0. Okay, sorry, it will be Q. So if reset equal to 1, then Q equal to 0. This is not S, this will be Q. Because we haven't defined the S variable in here. So it will be Q. So Q equal to 0 and reset equal to 1. And else if clock tick event and clock equal to 1 means when the positive age of clock occurs, then Q equal to D. This is the expression we know. And we will end the if statement, and we will end after that we will end the process statement, and we will end the behavioral statement. So like this, we can write the code of T flip. Next part. Now we will see for T flip flop. Like in T flip flop, we know that the truth table of T flip flop, like when T equal to 0, it will hold the previous output, and when T equal to 1, it will toggle the previous output. Like when there is T equal to 1 and previous output is 0, so it will be now new output will be 1. So T equal to 0 and previous output is 0, so it will be 0 because it will hold the case for T equal to 0. It has to push T, clock, and reset, and output will be Q and Q. So we will see this. So we will declare the libraries, and after that, the library definition, we will create entity T flip flop, and we will define the input ports like T, clock, and reset are our input, and Q is our output port, and we will enter entity. And after the entity, we will define the architecture or architecture of T flip flop. So, and we like here we have considered signal as STD logic. Like we have taken a variable S. So we'll process like we will see what is the use of this variable. And we will begin the architecture. Here process clock and reset. So after processing clock and reset, and we will begin. If reset equal to 1, then the S equal to 0. Like you can see here S equal to 0. We are not writing Q because we have taken the S as a variable. So we are storing the result of Q in S. So like you will see in further. So S equal to 0, and after that else if clock tick event and clock equal to 1, then T equal to 1 means when the at the positive rising age of clock, this means we are saying if T equal to 1, S equal to not S. Means if T is high, so we know that then it will toggle. So S equal to not S. We understand this. And else if else if S is T equal to 0, then it will hold the previous output. So S will be equal to S, and there are two if statement like if and if. So we will end this both. We will end if statement 2 times, and at last we will transfer our result from S to Q variable. So after that we will end process statement and end behavioral statement. Now we will see JK flip flop. So similarly, JK flip flop has one clock, JK, and these are inputs, and Q is an output variable. So when this is a truth table of JK flip flop, when J and K are 0, 0, then it will hold the previous output, and when J0 K1, the Q will be 0. When J1, the Q will be high. When J1 K1, then it will toggle the previous output. So means you can say in JK flip flop our T flip flop is also included. Like here, see this condition and this condition. Here it is holding the output. Here it is the toggling the output. Now we will try to write the code of JK flip-flop. So first of all, we will declare the libraries, attribute libraries, and after that we will create entity, and we will declare the as input like JK clock and reset as input and Q as our output. And after entity declaration, we will declare the architecture, and we will consider same and like in previous example here, same signal as, and after considering as, we will process our inputs clock and reset, and if reset equal to 1, then the s equal to 0, means when reset is high or output is 0. And else if at the positive edge of clock, if j here we simply implemented our truth table like j0 k0, then s equal to s, it will hold the output. Else if j0 k1, it s equal to 0. Else if j1 k1, s equal to 1. Else if j1 k1, not s, so it will toggle the previous output. So here we are implementing, in this part we are implementing our truth table, like you can see clearly. These are the 4 conditions. After that, we will end if statement 2 times, and at last we will transfer our result from s to q variable, and we will end the process statement and behavior. So like this, you can design the JK flip-flop, and similarly, we can design any flip-flop like SR flip-flop. I haven't taken here, so but you can design similar like SR flip-flop and master slave flip-flop, any type of flip-flop, any type of combinational circuit. Like you can design. I have taken the example of 2 raised to 4 mux, so you can design any mux like 4 raised to 1 to 60 raised to 1, any type of mux, 4 raised to 1, 60 raised to 1, any type of mux which you want. And similarly, you can design the any type of decoder by in using the similar type of person. So thank you. That's all for this video.